At the edge of a black hole, reality itself seems to unravel, where the familiar rules of time and space bend and twist into something unrecognizable. This is the cosmic event horizon, a boundary so strange, so mysterious, that it defies everything we think we know about the universe. What happens there? What lies beyond that point where light itself can't escape? These are questions that have puzzled scientists and stargazers alike for decades. But the answers might hold more than just scientific curiosity. They could reshape our understanding of existence itself. In this video, we'll journey to the very edge of these enigmatic phenomena, exploring the mind-bending physics, the cutting-edge theories, and the tantalizing possibilities that could unlock secrets about the origins of the universe. So, get ready to dive into one of the most fascinating mysteries of the cosmos, because what happens at the edge of a black hole is far stranger than you might imagine. Picture standing at the edge of a waterfall, feeling the pull of the water as it cascades into the unknown below. Now, imagine that same sensation, but instead of water, you're dealing with the relentless grip of gravity. This is the event horizon, a boundary so profound that once crossed, there's no turning back. At this edge of a black hole, gravity becomes so intense that not even light can escape its pull. It's not a physical surface you can touch or see. Instead, it's a region in spacetime where the rules of our universe begin to unravel. Crossing this invisible threshold means leaving behind everything familiar, entering a realm where the laws of physics as we know them no longer apply. The event horizon is more than just a boundary, it's a gateway offering a glimpse into some of the deepest mysteries of the cosmos. What lies beyond this edge? What happens to matter and energy once they cross over? These are the questions that keep scientists and stargazers alike captivated, and they're just the beginning of our journey into the unknown. As we venture closer to the edge of a black hole, gravity becomes the dominant force, shaping everything in its vicinity. Here, the pull of gravity isn't just strong, it's unimaginably intense, warping the very fabric of spacetime itself. This isn't the gentle tug you feel on Earth. It's a force so powerful it can bend light and twist time into unrecognizable forms. Picture spacetime as a stretched sheet and a black hole as a heavy ball placed on it. The sheet bends dramatically, creating a steep curve that draws everything toward the center. Near a black hole, this curve becomes so extreme that nothing, not even light, can escape once it crosses the event horizon. One of the most fascinating effects of this gravitational pull is something scientists call spaghettification. Imagine an object like a spaceship or even a star drifting too close to the black hole. The gravitational force on the side nearest to the black hole is exponentially stronger than on the far side. This difference stretches the object like a piece of taffy, pulling it into a long, thin strand. At the same time, the immense pressure compresses it sideways. It's a gruesome yet awe-inspiring process that showcases just how extreme these conditions are. But gravity's influence doesn't stop there. It also warps the passage of time itself. If you were to observe someone falling toward a black hole, you'd notice something bizarre. From your perspective, time for them would appear to slow down, almost as if they were moving in slow motion. To them, however, everything would seem normal until they reach the point of no return. This time dilation effect is one of the many ways black holes challenge our understanding of the universe, pushing the boundaries of physics to its limits. And then there's light. As it approaches the edge of a black hole, light doesn't just bend. It behaves in ways that defy intuition. It gets trapped in orbits, creating what's known as a photon sphere, a region where light can actually circle the black hole multiple times before either escaping or being swallowed. These strange behaviors of light give us clues about the nature of black holes and the extreme conditions at their edges. But what exactly happens to light as it crosses the event horizon? That's a mystery we'll explore next, As we approach the edge of a black hole, light itself begins to defy our everyday understanding of physics. One of the most striking phenomena here is gravitational lensing. Imagine light from a distant star passing close to the black hole. Instead of traveling in a straight line, the immense gravity bends the light's path, twisting and distorting it like a cosmic funhouse mirror. This creates bizarre visual distortions where background stars and galaxies appear stretched, smeared, or even duplicated around the black hole's silhouette. But that's just the beginning. As light ventures closer to the event horizon, it undergoes a dramatic shift known as redshift. This happens because the black hole's gravity is so intense that it stretches the light waves, shifting them toward the red end of the spectrum. The closer the light gets, the more extreme the redshift becomes, until eventually it becomes invisible to our eyes, trapped forever in the black hole's grasp. Perhaps the most haunting visual effect occurs in a region called the photon sphere. Here, light doesn't just bend, it can actually orbit the black hole. Picture a glowing halo of light circling endlessly, caught in a cosmic dance with gravity. This eerie phenomenon creates surreal visual effects, like a black hole seemingly wrapped in a ring of fire. It's as if the black hole is wearing a crown of trapped photons, a breathtaking yet otherworldly sight. Beyond these visual wonders lies the concept of the black hole's shadow. This isn't a shadow in the traditional sense, but rather a dark void surrounded by a glowing ring of light. That ring, known as the photon ring, is formed by light bent around the black hole. Scientists have used this shadow to capture the first ever image of a black hole, providing groundbreaking insights into these cosmic giants. By studying the shadow, researchers can measure the black hole's size, shape, and even the speed of its rotation. Yet, even as we marvel at these visual mysteries, we're reminded that the edge of a black hole is where the laws of quantum mechanics come into play. This strange intersection of gravity and quantum physics holds the key to understanding what truly happens at the brink of the unknown. Now, let's shift our gaze to one of the most mind-bending collisions in science: quantum mechanics meeting black holes. At first glance, these two fields seem worlds apart. Quantum mechanics deals with the tiniest particles and their bizarre behaviors, while black holes are cosmic giants governed by gravity's unrelenting pull. But when they intersect, the results are nothing short of astonishing. Here's where Hawking radiation enters the picture. Proposed by Stephen Hawking in the 1970s, this theory suggests that black holes aren't entirely black after all. At the very edge of a black hole, pairs of particles and antiparticles pop in and out of existence, a normal quantum phenomenon. Usually, these pairs annihilate each other almost instantly. But near a black hole, something extraordinary happens. One particle falls in while the other escapes, carrying energy away from the black hole. Over time, this process causes the black hole to lose mass and eventually evaporate. This discovery was revolutionary because it challenged the long-held belief that nothing, not even light, could escape a black hole's gravitational grip. Suddenly, black holes weren't just cosmic vacuums, they were leaking energy, albeit very slowly. But this raises a profound question. If black holes eventually evaporate, what happens to all the information they've swallowed? In quantum mechanics, information is never truly lost, but black holes seem to defy this principle, creating what's known as the information paradox. So, what does this mean for the universe? Could the gradual evaporation of black holes reveal new truths about the fabric of reality? Or does this paradox hint at deeper laws of physics we've yet to uncover? As we venture further, this mystery only deepens, leading us to another fascinating puzzle: the information paradox, and what it means for the ultimate fate of the cosmos. Picture this: you're holding a book, one filled with every detail of the universe's history. Now imagine tossing it into a black hole. According to classical physics, that book, and all the information it contains, would be lost forever, swallowed by the black hole's infinite gravitational pull. But here's where things get mind-bending. Quantum mechanics tells us that information can never truly be destroyed. It's a fundamental rule of the universe. So what happens to that book? Does it vanish or does it somehow survive? This is the heart of the black hole information paradox, a puzzle that has left physicists scratching their heads for decades. The paradox lies in the clash between two of the most successful theories in physics: general relativity and quantum mechanics. General relativity, Einstein's masterpiece, suggests that anything crossing the event horizon of a black hole is gone for good, with no trace left behind. But quantum mechanics insists that information, like the story in that book, must be preserved. If it's lost, it would throw the very foundation of quantum theory into chaos. On the other hand, if information is preserved, it challenges our understanding of black holes and spacetime itself. It's a cosmic tug of war with no clear winner. This paradox has sparked some fascinating theories. One leading idea is the holographic principle, which suggests that all the information that falls into a black hole isn't actually lost. It's encoded on the event horizon like a hologram. Think of it as a giant cosmic DVD, storing every detail of what's been consumed. Another wild concept is the firewall hypothesis, which proposes that a blazing wall of energy sits just inside the event horizon, incinerating anything that crosses it. This would preserve information, but at the cost of violating Einstein's equivalence principle, the cornerstone of general relativity. As we wrestle with these theories, one thing becomes clear: the edge of a black hole isn't just a boundary in space, it's a frontier of time. And that brings us to the next piece of the puzzle. What role does time play in this cosmic mystery? How does it bend, stretch, or even break at the edge of a black hole? The answers might be even stranger than the questions themselves. Picture an astronaut drifting closer and closer to a black hole. From their perspective, time feels normal. Every second ticks by just as it always has. But for someone watching from a safe distance, the story is entirely different. Time for the astronaut seems to slow down, stretching moments into what feels like an eternity. This bizarre phenomenon is known as time dilation, a cornerstone of Einstein's theory of relativity. As the astronaut nears the event horizon, the point of no return, time for them grinds almost to a halt compared to the outside universe. It's as if the black hole is tugging on the very fabric of time itself. What's even more fascinating is the scale of this effect. For every minute the astronaut experiences, years or even decades could pass for those of us watching from afar. This isn't just science fiction, it's a real, measurable consequence of the immense gravitational pull of a black hole. But what does this mean for our understanding of time? It challenges everything we think we know about how time flows. Time isn't a constant, universal force, it's flexible, shaped by the gravity and motion of the objects around it. This strange behavior of time near black holes also raises practical questions for space exploration. If we ever attempt to travel near these cosmic giants, how would we account for the drastic difference in time experienced by astronauts and those back on Earth? It's a puzzle that underscores just how alien and incomprehensible black holes truly are. And speaking of puzzles, this leads us to another mind-bending concept: wormholes. Could these theoretical tunnels through space-time offer a way to bend the rules of time and distance? Let's explore that possibility next. As we peer into the mysteries of black hole edges, one of the most tantalizing ideas emerges. Could these cosmic giants harbor the secrets to wormholes? The concept of a wormhole, a theoretical tunnel through space-time, has long captured our imagination, offering the possibility of shortcuts across the universe or even gateways to entirely different realities. But how could a black hole, known for its immense gravitational pull, play a role in creating such a phenomenon? At the edge of a black hole, where the fabric of space-time is stretched to its limits, some theories suggest that extreme conditions might allow for the formation of wormholes. These hypothetical tunnels could connect distant points in space, bypassing the vast distances that light would take to travel through normal space. Imagine stepping into a black hole's event horizon and emerging light years away, or perhaps in a completely different universe. While this sounds like science fiction, it's grounded in the mathematics of Einstein's general theory of relativity. However, there's a catch. For a wormhole to remain stable, it would require something called exotic matter, a mysterious substance with negative energy that defies the usual rules of physics. This exotic matter would counteract the intense gravitational forces trying to collapse the wormhole, keeping it open long enough for anything to pass through. The problem: we've yet to discover any evidence that such matter exists. Without it, wormholes remain a fascinating but unproven possibility. This brings us to the broader role of black holes in shaping the cosmos. While wormholes remain speculative, black holes themselves are undeniably real and play a crucial part in the formation of galaxies. Their immense gravitational influence can dictate the movement of stars and gas, acting as the engines that drive the evolution of entire galactic systems. And as we continue to explore these cosmic wonders, we uncover not just the secrets of black holes, but also the potential for entirely new ways of understanding the universe. At the heart of nearly every galaxy lies a supermassive black hole, a colossal force that shapes its surroundings in profound ways. These black holes, millions or even billions of times more massive than our Sun, are not just passive cosmic vacuums, they are active architects of galactic evolution. Their immense gravitational pull influences the motion of stars, gas, and dust, creating a dynamic environment where galaxies grow and transform over billions of years. But how exactly do these titans at the center of galaxies drive such widespread change? The answer lies just beyond the edge of the black hole itself, the event horizon. The event horizon acts as a gatekeeper, regulating the flow of matter and energy into the black hole. As gas and debris spiral inward, they form what's known as an accretion disk, a swirling ring of superheated material that emits enormous amounts of light and radiation. This process doesn't just feed the black hole, it also sends out powerful jets of energy that can travel across vast distances, influencing the structure of the galaxy. These jets can compress nearby clouds of gas, triggering the formation of new stars and even planetary systems. In this way, the black hole's edge becomes a cosmic engine, driving the cycle of creation and destruction on a galactic scale. Interestingly, black holes don't just consume, they also contribute to the birth of stars and planets. The energy they release can heat surrounding gas clouds, causing them to collapse into dense regions where star formation begins. Over time, these stars may form planets, continuing the cycle of cosmic evolution. It's a delicate balance. While the black hole's gravity pulls matter inward, its energy output can push material outward, shaping the galaxy in a complex interplay of forces. This intricate relationship between black holes and their host galaxies raises even more intriguing questions. What happens to the matter that crosses the event horizon? Where does it go and what becomes of it? These questions lead us to one of the most mysterious concepts in astrophysics, the singularity. At the very heart of a black hole lies one of the most perplexing mysteries in all of astrophysics, the singularity. This is the point where all the mass of the black hole is compressed into an infinitely dense, infinitely small space. It's a place where the rules of physics as we know them seem to come to an abrupt halt. Gravity becomes so intense that space and time themselves warp beyond recognition, creating conditions that challenge our understanding of reality. But here's the catch: we can't actually see the singularity. It's hidden behind the event horizon, the black hole's boundary of no return. Once anything crosses that line, it's lost to us forever, leaving the singularity shrouded in mystery. This raises a fascinating question: what really happens inside a black hole's core? According to Einstein's theory of general relativity, the singularity is where the math breaks down, where our equations simply stop making sense. It's a point of infinite density and zero volume, a concept that defies our everyday experiences and even our scientific frameworks. Some theories suggest that quantum mechanics might hold the key to understanding what's going on there, but for now, the singularity remains one of the universe's greatest enigmas. Black holes, with their singularities and event horizons, aren't just cosmic oddities, they play a crucial role in shaping the universe itself. As we move into the next part of our journey, we'll explore how these gravitational giants influence the expansion and evolution of the cosmos, connecting the mysteries of the infinitesimal to the vastness of space itself. As we peer deeper into the cosmos, one of the most profound questions arises. How do black holes, those enigmatic regions of extreme gravity, shape the universe itself? It's a question that ties together the very large and the unimaginably dense. When we think about the universe's expansion, black holes might seem like isolated phenomena, but recent theories suggest they could play a pivotal role in the fate of everything around us. Scientists have long known that the universe is not just expanding, it's accelerating. This mysterious force driving this acceleration is called dark energy. But where does dark energy come from? Some researchers propose that black holes might hold a clue. As black holes grow, swallowing matter and energy, they could be subtly influencing the fabric of spacetime in ways that contribute to this cosmic push. It's almost as if these cosmic vacuum cleaners are also architects, shaping the universe's destiny on a scale we're only beginning to understand. This isn't just about black holes as individual objects, it's about their collective impact. Imagine the universe as a tapestry, with black holes as knots that pull and stretch the threads of spacetime. Over billions of years, their combined gravitational influence could be one of the keys to understanding why galaxies are moving apart faster and faster. It's a theory that bridges the microscopic world of quantum physics with the vastness of cosmology, offering a tantalizing glimpse into how the universe might evolve. But the story doesn't stop there. Some scientists are even exploring the idea that black holes could be gateways to other universes, hinting at a multiverse where our cosmos is just one of many. These theories suggest that black holes might not only influence the expansion of our own universe, but also connect it to others. Imagine a network of universes, each with its own laws of physics, all linked by these gravitational behemoths. While this idea is still in the realm of speculation, it opens up breathtaking possibilities for what lies beyond the edge of a black hole and beyond the boundaries of our understanding. As we continue to unravel these mysteries, one thing is clear: black holes are far more than just cosmic oddities. They might be the architects of the universe's expansion, the bridges to other realities, and the keys to answering some of the most profound questions in science. What lies beyond their event horizons? What role do they play in the grand tapestry of existence? These are the questions that drive us to keep exploring, keep questioning, and keep marveling at the wonders of the cosmos. What if black holes aren't just cosmic vacuums, but something far more extraordinary? Could they be gateways to entirely different universes? This idea isn't just science fiction, it's a theory that has captivated scientists and philosophers alike. In the vast landscape of the multiverse, black holes might serve as bridges, connecting our universe to others in ways we're only beginning to imagine. The concept suggests that beyond the event horizon, where our understanding of physics breaks down, lies the potential for entirely new realms of existence. This idea isn't purely speculative. Some theories in quantum mechanics and general relativity hint at the possibility. For instance, the singularity at the center of a black hole might not be an endpoint but a doorway. If true, it would mean that black holes aren't just destroyers of matter but creators of new possibilities, opening pathways to universes with different physical laws, dimensions, or even timelines. The philosophical implications are profound. If black holes are portals, what does that mean for our understanding of reality? Are we just one of countless universes, each with its own unique story? The multiverse concept also raises questions about the nature of existence itself. If black holes can transport matter or even information to other universes, could they also be conduits for life? Could civilizations in one universe communicate or travel to another through these cosmic tunnels? While these ideas remain theoretical, they challenge us to think beyond the confines of our own universe and consider the grander tapestry of existence. Now, let's take this concept one step further. If black holes can connect us to other universes, could they also manipulate time? This brings us to another mind-bending possibility: black holes and time travel. Their immense gravitational pull doesn't just warp space, it warps time itself, creating conditions where time could flow differently. Could a black hole serve as a time machine, allowing us to journey backward or forward in time? One of the most mind-bending ideas in science is the concept that black holes could serve as gateways for time travel. It sounds like science fiction, but there's actual physics behind it. According to Einstein's theory of general relativity, the intense gravity of a black hole warps space and time so drastically that it could create what's known as a wormhole, a theoretical tunnel connecting two distant points in spacetime. If such a tunnel exists and remains stable, it could theoretically allow for time travel, either into the past or the future. But here's the catch: the challenges and paradoxes involved are staggering. For starters, the extreme gravitational forces near a black hole would likely tear apart anything or anyone that ventured too close. Even if survival were possible, the journey would raise questions like the famous grandfather paradox, where changing the past could create logical contradictions that defy our understanding of cause and effect. And then there's the question of stability. Wormholes, if they exist, are thought to be incredibly fragile, requiring exotic forms of matter to keep them open. The energy needed to sustain such a passage is beyond anything we can currently imagine, let alone produce. So while the idea of using black holes as time machines is fascinating, it remains firmly in the realm of theory, at least for now. But what if black holes play a role not just in traversing time, but in the very origins of life itself? This brings us to the next intriguing possibility: the idea that black holes might have been instrumental in shaping the conditions necessary for life to emerge in the universe. Black holes, often thought of as cosmic destroyers, might hold an unexpected secret. They could be key players in the creation of life itself. It's a strange idea at first. How could these regions of immense gravity, where even light cannot escape, contribute to the development of life-supporting environments? The answer lies in their role as cosmic recyclers. When black holes consume matter, they don't just trap it forever. Through processes like jets and radiation, they eject energy and elements back into the surrounding universe. This includes the heavy elements like carbon, nitrogen, and oxygen, essential building blocks for planets and, ultimately, life. Without black holes, the universe might be a much simpler place. During their violent interactions with stars and galaxies, black holes distribute these crucial elements across vast distances, seeding future star systems with the ingredients necessary for life to emerge. It's almost as if black holes are the universe's way of spreading the raw materials for planets like Earth to form. This distribution of energy and matter isn't just random, it's a delicate dance that shapes the cosmic landscape, creating pockets of potential where life could one day flourish. And this leads us to an even bigger question: could black holes also play a role in the search for extraterrestrial intelligence? If they're responsible for dispersing the elements needed for life, it's possible that the regions around black holes could be hotspots for habitable worlds. Imagine civilizations developing near these cosmic giants, harnessing their energy or even using them as markers in their exploration of the universe. Black holes might not just be silent observers of the cosmos, they could be active participants in the story of life itself. black holes, those enigmatic titans of the universe, might hold secrets not just about the cosmos, but also about the possibility of life beyond our planet. Could these gravitational powerhouses play a role in the search for extraterrestrial intelligence? Scientists have long speculated that advanced civilizations, far beyond our current technological capabilities, might harness the immense energy of black holes to fuel their societies. Think about it, black holes aren't just cosmic vacuum cleaners, they're also potential energy gold mines. The accretion disks around them emit staggering amounts of radiation, and the gravitational forces could be tapped as a virtually limitless power source. If a civilization mastered this technology, it could thrive on a scale we can barely comprehend. But how would we even begin to detect such a civilization? One intriguing idea is to look for technosignatures, unusual patterns of energy or light that can't be explained by natural processes. For instance, a black hole surrounded by artificial structures designed to capture its energy might emit distinct signals detectable across vast distances. This could be our first clue that we're not alone in the universe, and let's not forget the bigger picture. Black holes are not isolated entities. They're woven into the cosmic web, the intricate network of matter and dark matter that shapes the universe. These gravitational behemoths act as cosmic anchors, influencing the flow of galaxies and the distribution of life-supporting elements. Understanding their role in this grand tapestry could help us pinpoint regions of the universe where life is more likely to emerge. As we continue our search for extraterrestrial intelligence, black holes may just be the signposts guiding us toward the answers we seek. As we zoom out from the mysterious edges of black holes, we find ourselves staring at something even more vast and intricate: the cosmic web. Picture this, an enormous network of dark matter and gas, stretching across the universe like threads of a spider's silk. Black holes, it turns out, are not just isolated monsters lurking in the darkness. They're key players in this cosmic tapestry, connecting galaxies and shaping the very structure of space itself. Think of the cosmic web as the universe's skeleton, with galaxies clustering along its strands like beads on a string. Black holes, especially supermassive ones at the centers of galaxies, act as cosmic anchors. Their immense gravitational pull helps bind galaxies together, influencing how they move and interact within this colossal network. But it doesn't stop there. Black holes also drive the flow of gas and energy along the web, feeding star formation and even triggering the birth of new galaxies in some cases. It's a dynamic, ever-evolving process that has shaped the universe over billions of years. What's truly fascinating is how black holes contribute to the universe's large-scale structure. When black holes merge, they send ripples through space-time gravitational waves that can subtly alter the distribution of matter in the cosmic web. These ripples, though faint, play a role in how galaxies cluster and evolve over time. Plus, the jets of energy ejected by active black holes can push gas out into the farthest reaches of the web, seeding the conditions for future cosmic growth. But as we marvel at this intricate interplay, it's worth asking, what does this mean for the universe's ultimate fate? Black holes, in their own destructive yet creative way, may hold the key to understanding how the cosmos will evolve over trillions of years. Will they continue to shape galaxies and fuel the cosmic web, or will they eventually consume everything in their path? The answers lie in the delicate balance between creation and destruction, a dance that defines the very essence of our universe. As we peer into the distant future of the universe, black holes emerge as key players in a cosmic drama that spans trillions of years. One of the most fascinating theories about their role involves the ultimate fate of the cosmos, the heat death of the universe. This concept describes a state where the universe reaches maximum entropy, a cold, dark expanse where no energy is left to sustain stars, galaxies, or any form of life. But how do black holes fit into this scenario? The answer lies in a process discovered by Stephen Hawking, known as Hawking radiation. Over unimaginable timescales, black holes are not eternal. They slowly lose energy, emitting particles through this radiation. This means that even the most massive black holes, those that dominate galaxies, will eventually evaporate. As they do, they release the last vestiges of energy back into the universe, accelerating its journey toward heat death. It's a profound thought. Black holes, often seen as the ultimate cosmic destroyers, may also be the final architects of the universe's demise. This evaporation process, though incredibly slow, is a stark reminder that nothing in the cosmos lasts forever, not even the mightiest black holes. And as we ponder this, we're drawn to the next intriguing question: what happens to the universe when the last black hole fades away? At first glance, black holes seem like the ultimate cosmic vacuums, sucking in everything around them with no escape. But what if I told you that even these mysterious giants don't last forever? Enter one of the most fascinating ideas in modern physics: black hole evaporation. This process, driven by a phenomenon called Hawking radiation, suggests that black holes aren't eternal after all. Over unimaginable stretches of time, they can slowly shrink, losing mass until they eventually vanish. So how does this work? Picture the boundary of a black hole, known as the event horizon. According to Stephen Hawking's groundbreaking theory, pairs of particles and antiparticles constantly pop into existence near this edge. Normally, they annihilate each other almost instantly. But at the event horizon, one particle can fall into the black hole while the other escapes into space. This escaping particle is Hawking radiation. Over eons, this radiation siphons away energy from the black hole, causing it to lose mass and eventually evaporate completely. But don't expect this to happen anytime soon. The process is incredibly slow, especially for massive black holes. A black hole with the mass of our Sun would take trillions upon trillions of years to evaporate. For supermassive black holes, the timeline stretches to numbers so vast they're almost impossible to comprehend. While this might seem like a concept far removed from our daily lives, it has profound implications for the universe. Black hole evaporation suggests that even the most dominant forces in space have an expiration date, reshaping our understanding of cosmic timelines. As we ponder the far-off fate of black holes, it's worth considering their role in shaping the universe on a grander scale. These enigmatic objects don't just exist in isolation, they influence the structure of the cosmos itself. The regions where black holes reside often become centers of cosmic voids, vast empty spaces that stretch across the fabric of the universe. The interplay between black holes and these voids is a fascinating area of study, hinting at the intricate dance of forces that govern the cosmos. Black holes aren't just cosmic vacuum cleaners, they're also architects of the universe's largest structures. One of the most fascinating ways they shape the cosmos is through their potential role in creating cosmic voids, those vast, seemingly empty regions that stretch across the universe. These voids are not just random gaps, they're part of the intricate web of matter and space that defines the universe's large-scale structure. But how do black holes play a part in this? When massive black holes collide or merge, they release incredible amounts of energy in the form of gravitational waves. These waves ripple through space-time, redistributing matter in their wake. Over billions of years, this process can push matter away from certain areas, leaving behind enormous voids. Additionally, the intense gravitational pull of black holes can draw in nearby matter, further clearing out regions of space. The result, these cosmic voids become the empty arenas surrounded by dense clusters of galaxies like bubbles in a frothy sea. But the story doesn't end there. Some theories suggest that black holes might even play a role in the birth of entirely new universes. This idea comes from the concept of black hole singularities, points where the laws of physics as we know them break down. Inside a singularity, it's possible that conditions could become so extreme that they trigger the creation of a new universe, branching off from our own. While this remains speculative, it's a tantalizing thought that black holes could be not just destroyers of matter, but also creators of entirely new cosmic realms. As we explore these mind-bending possibilities, it's clear that black holes are far more than just mysterious objects lurking in the depths of space. They're active players in the ongoing story of the universe, shaping everything from vast cosmic voids to potentially birthing new realities. And as we continue to unravel their secrets, we might just find ourselves looking into a mirror that reflects the very origins of existence itself. What if the darkness of a black hole isn't an end but a beginning? Some scientists have proposed a mind-bending theory. Black holes might be the seeds from which entirely new universes emerge. Picture this: every time a black hole forms, it could be the spark that ignites a fresh cosmic system, expanding into its own space and time. This idea isn't just science fiction. It's rooted in the mathematics of general relativity and quantum mechanics, suggesting that the intense gravitational collapse of a black hole might create the conditions for a new universe to bloom within its heart. This raises profound philosophical questions. If black holes are giving birth to new universes, does that mean our own cosmos began inside a black hole elsewhere? Could there be an infinite nesting of universes, each birthed within the singularity of another? This concept challenges our understanding of existence itself, blurring the line between destruction and creation. After all, what we perceive as the end of matter and light in a black hole might instead be the genesis of something entirely new. But this isn't just a thought experiment. The idea has implications for how we study the universe. If black holes are indeed cosmic creators, they might hold clues to the nature of reality itself. For instance, could the mysterious dark matter that makes up most of the universe's mass be connected to these processes? As we delve deeper into the mysteries of black holes, we're not just exploring the edges of our own universe, we're potentially peering into the birthplaces of others. This brings us to the next frontier, the role of black holes in understanding the enigmatic substance known as dark matter. As we peer deeper into the mysteries of the cosmos, one of the most intriguing connections lies between black holes and dark matter, the invisible substance thought to make up roughly 85% of the universe's mass. While dark matter doesn't emit, absorb, or reflect light, its presence is inferred by the gravitational effects it has on galaxies and larger cosmic structures. Black holes, with their immense gravitational pull, might just hold the key to unraveling some of the secrets of this elusive material. The gravitational influence of black holes could act as a cosmic magnifying glass, distorting the light from distant objects in a phenomenon known as gravitational lensing. This distortion can help astronomers map the distribution of dark matter around black holes and in the surrounding regions of space. By studying how light bends around these massive objects, scientists can infer where dark matter is concentrated and how it behaves on a cosmic scale. It's like using the shadows cast by black holes to illuminate the invisible web of dark matter that threads through the universe. But the relationship between black holes and dark matter goes even further. Some theories suggest that black holes could be actively interacting with dark matter, potentially even capturing and accumulating it within their event horizons. This interaction might provide clues about the nature of dark matter particles, helping scientists test whether they behave as predicted by current models or if entirely new physics is at play. As we explore this connection, it's impossible to ignore another cosmic enigma: dark energy, the mysterious force driving the accelerated expansion of the universe. Black holes, with their role in shaping the cosmos and influencing the behavior of matter on the largest scales, could also offer insights into this puzzling phenomenon. Their interactions with dark matter might indirectly shed light on how dark energy operates, opening new avenues for understanding the forces that govern the universe's fate. This interplay between black holes, dark matter, and dark energy represents one of the most fascinating frontiers in modern astrophysics. By studying these cosmic giants, we're not just learning about black holes themselves, we're uncovering the hidden threads that weave the fabric of the universe. The universe is expanding faster than we ever expected, and behind this mysterious acceleration lies a force called dark energy. But what if black holes, those enigmatic cosmic giants, hold a key to understanding this phenomenon? Recent theories suggest that black holes might be intimately connected to dark energy, the very force shaping the fate of our universe. Scientists are exploring how these gravitational behemoths could influence the rate of cosmic expansion, potentially acting as cosmic engines that drive dark energy's effects. Some even propose that black holes might store or release energy in ways that contribute to the universe's ever-increasing scale. This intriguing link opens up a new frontier in astrophysics, where the study of black holes could shed light on one of the greatest mysteries of our time. And as we probe deeper into this connection, another fascinating discovery comes into focus: the role of black holes in the study of gravitational waves. These ripples in spacetime, first detected in 2015, offer a unique window into the behavior of black holes and the forces shaping our universe. Black holes aren't just cosmic vacuum cleaners, they're also incredibly dynamic objects capable of sending ripples across the fabric of spacetime itself. These ripples, known as gravitational waves, are produced when black holes collide or merge, creating disturbances that travel outward at the speed of light. It's like dropping a pebble into a pond, except instead of water, the waves ripple through the very structure of the universe. In 2015, scientists made history by detecting gravitational waves for the first time, confirming a prediction made by Albert Einstein a century earlier. This monumental discovery opened up an entirely new way of observing the cosmos, allowing us to hear the universe in ways we never could before. The significance of detecting gravitational waves goes far beyond just proving Einstein right. These waves carry crucial information about the black holes that created them, details about their mass, spin, and even how they formed. By studying these ripples, we can piece together the stories of some of the universe's most extreme events, like the violent collisions of black holes billions of light years away. This has transformed our understanding of black holes, revealing them not as silent, static objects, but as active players in the cosmic symphony. But the impact of gravitational waves doesn't stop there. They also provide a unique window into the nature of spacetime itself, offering clues about how gravity operates on both the largest and smallest scales. This brings us to one of the most profound mysteries in modern physics: the connection between black holes and quantum gravity. While gravitational waves help us explore the macroscopic effects of gravity, the behavior of black holes at their very cores hints at a deeper quantum reality that we're only beginning to unravel. Black holes are not just cosmic mysteries, they're also laboratories for some of the most profound questions in physics. One of the biggest puzzles they help us tackle is the quest to unify quantum mechanics and general relativity. These two pillars of modern physics describe the universe in very different ways. General relativity explains the behavior of massive objects like stars and black holes, while quantum mechanics governs the tiny world of particles. But when it comes to black holes, especially at their cores, these theories seem to collide. That's where the concept of quantum gravity comes in. It's the theoretical framework that scientists hope will bridge the gap between these two realms. And black holes, with their extreme gravitational fields and bizarre properties, are the perfect testing ground for these ideas. At the very heart of a black hole lies a singularity, a point where gravity becomes infinite and the laws of physics as we know them break down. This is where quantum gravity becomes essential. While general relativity predicts the existence of singularities, it can't describe what happens there. Quantum mechanics, on the other hand, might offer clues, but it doesn't yet account for gravity on such a scale. This is why black holes are so crucial. They force us to confront the limitations of our current theories and push us toward a deeper understanding of the universe. but the story doesn't stop there. Black holes also play a key role in the study of spacetime singularities. These are not just features of black holes, they're thought to have existed at the birth of the universe during the Big Bang. By examining how singularities behave in black holes, scientists hope to shed light on the origins of the cosmos itself. It's a fascinating connection that ties the largest structures in the universe to its smallest, most fundamental aspects. So, as we continue to explore the edge of black holes, we're not just learning about these enigmatic objects, we're uncovering the very fabric of reality. And that's a journey that takes us from the depths of space to the building blocks of existence itself. At the very core of a black hole lies a phenomenon that defies everything we know about the universe, a space-time singularity. This is a point where gravity becomes infinitely strong, space and time effectively cease to exist, and the laws of physics as we understand them simply break down. It's a place where the rules of classical physics and even Einstein's theory of relativity reach their limits, leaving scientists with more questions than answers. Singularities are not just theoretical curiosities, they represent the ultimate boundary of our understanding, a frontier where the universe seems to hide its deepest secrets. Studying these singularities is no easy task. For one, they're hidden behind the black hole's event horizon, the point of no return where not even light can escape. This makes direct observation impossible, leaving scientists to rely on mathematical models and theoretical predictions. But even these tools have their limits. At the singularity, the equations of general relativity predict infinite density and curvature, which are physically nonsensical results. This suggests that our current theories are incomplete and that new physics, perhaps a unified theory of quantum gravity, is needed to unravel the mystery. The implications of singularities go far beyond black holes. They challenge us to rethink the nature of reality itself. If space and time can break down in such extreme conditions, what does that mean for the universe as a whole? Could singularities be gateways to other regions of spacetime, or do they mark the end of existence as we know it? These questions push the boundaries of both science and philosophy, inviting us to explore the unknown with a mix of curiosity and humility. As we grapple with the enigma of singularities, another fascinating concept emerges: black hole thermodynamics. This field bridges the gap between gravity and quantum mechanics, revealing surprising connections between black holes and the laws of thermodynamics. It's a reminder that even in the most extreme environments, there are patterns and principles waiting to be uncovered. And it's here, at the intersection of these two ideas, that we begin to see how black holes might hold clues to the fundamental nature of the universe itself. As we venture deeper into the enigmatic world of black holes, we stumble upon a fascinating intersection of astrophysics and thermodynamics. You might wonder, how can something as immense and mysterious as a black hole be compared to the laws that govern heat and energy? Well, black hole thermodynamics offers a surprising perspective. Just like any thermodynamic system, black holes have properties that can be described in terms of temperature, entropy, and energy. This connection was first unveiled in the early 1970s when physicists like Stephen Hawking and Jacob Bekenstein discovered that black holes aren't just cosmic vacuum cleaners. They're complex systems with their own set of rules. At the heart of this concept lies black hole entropy, a measure of the disorder or randomness within a black hole. While entropy might seem like an abstract idea, it's incredibly significant. In fact, Bekenstein proposed that the entropy of a black hole is proportional to the area of its event horizon. This means the larger the black hole, the more entropy it contains. But why does this matter? Because entropy is tied to information. In the universe, information is never truly lost, it's just rearranged. Black hole thermodynamics suggests that even when matter falls into a black hole, the information it carries isn't destroyed. Instead, it's encoded on the event horizon in a way that preserves the universe's fundamental laws. this idea has profound implications for our understanding of physics. It bridges the gap between quantum mechanics and general relativity, two fields that have long seemed incompatible. By studying black hole thermodynamics, scientists are uncovering clues about the nature of spacetime, gravity, and even the origins of the universe itself. And as we explore these principles, we're led to another intriguing question. How do black holes fit into the larger framework of cosmic censorship? This concept proposes that the universe has a way of hiding singularities, the infinitely dense cores of black holes, from our view, preserving the predictability of physics. Together, black hole thermodynamics and cosmic censorship offer a glimpse into the universe's deepest secrets, reminding us that even the most extreme phenomena are governed by elegant, universal laws. But what if a black hole's singularity, its infinitely dense core, wasn't hidden at all? What if we could somehow see it? This is where the cosmic censorship hypothesis comes into play. Proposed by physicist Roger Penrose, this idea suggests that nature has a built-in safeguard. Singularities are always cloaked by event horizons, the ultimate cosmic curtain. Without this protective veil, the extreme physics at the heart of a black hole could wreak havoc on the laws of the universe as we know them. The cosmic censorship hypothesis isn't just a fascinating thought experiment, it has profound implications for our understanding of reality. If true, it means the universe actively prevents singularities from being exposed, ensuring that the bizarre and unpredictable behavior at the center of a black hole remains isolated. This idea reinforces the notion that certain boundaries in the cosmos are there for a reason, preserving the predictability and order we've come to rely on in physics. Yet, as intriguing as this hypothesis is, it's not without its challenges. Some theoretical models suggest that under extreme conditions, such as the collision of two black holes, the event horizon might break down, potentially exposing the singularity. This raises questions about whether cosmic censorship is an absolute rule or more of a cosmic guideline. As we ponder the mysteries of singularities and event horizons, another fascinating concept emerges, the idea of black hole firewalls. These theoretical structures, lurking just outside the event horizon, could redefine our understanding of black hole interiors. Are they a last line of defense, or do they hint at an even deeper layer of cosmic secrets? Let's explore this next. What if the edge of a black hole isn't as serene as we once thought? Picture this. Instead of a smooth, uneventful crossing into oblivion, the event horizon might be a raging inferno, a so-called firewall that incinerates anything that comes too close. This radical idea challenges everything we thought we knew about black holes, and it all stems from a puzzle known as the information paradox. Black holes were long thought to be cosmic vacuums, swallowing everything including information without a trace. But quantum mechanics insists that information can never truly be lost. So where does it go? The firewall theory suggests that at the event horizon, a wall of unimaginable heat destroys anything falling in, preserving information in some form. It's a wild concept, but one that has sparked heated debates among physicists. If firewalls exist, they could completely rewrite our understanding of black holes and the fundamental laws of physics. But here's the twist, firewalls also raise more questions than they answer. For instance, if they're real, how do they form? And what does this mean for the fate of an astronaut falling into a black hole? Would they truly be burned to a crisp before even crossing the horizon, or is there more to the story? These questions don't just challenge our understanding of black holes, they push us to rethink the very nature of space, time, and reality itself. As we grapple with these mind-bending ideas, another intriguing possibility emerges, the connection between black holes and holography. Could the information destroyed at the firewall somehow be encoded on the surface of the black hole, like a cosmic hologram? This idea hints at a deeper link between the physics of black holes and the way our universe might fundamentally operate. At the heart of black hole physics lies one of the most fascinating and mind-bending ideas in modern science, the holographic principle. This concept suggests that all the information about the matter and energy swallowed by a black hole isn't lost deep within its core. Instead, it's encoded on the black hole's surface, its event horizon. Think of it like a cosmic version of a hologram, where a two-dimensional surface can hold the complete details of a three-dimensional object. In this case, the event horizon acts as that surface, storing the full story of everything that falls into the black hole. What's truly astonishing is how this principle reshapes our understanding of spacetime itself. If the holographic principle is correct, it implies that the universe we perceive as three-dimensional might actually be a projection of information encoded on a two-dimensional boundary. This idea challenges our most basic assumptions about reality, blurring the lines between space, time, and information. It's a concept that's as beautiful as it is perplexing, offering a new lens through which to view the cosmos. But the implications don't stop there. The holographic principle also provides a potential solution to the famous black hole information paradox, the question of what happens to information when it falls into a black hole. If all that information is encoded on the event horizon, it's not truly lost, just transformed. This opens up profound questions about the nature of reality and whether the universe itself might operate like a giant hologram. As we delve deeper into these ideas, we encounter another intriguing connection: the role of black holes in the study of quantum entanglement. The way information is encoded on a black hole's surface bears striking similarities to the entangled states of particles in quantum mechanics. These parallels could hold the key to unifying the two great pillars of modern physics, general relativity and quantum mechanics, into a single, coherent theory. As we venture deeper into the mysteries of black holes, we encounter one of the most perplexing puzzles in modern physics: the relationship between black holes and quantum entanglement. Picture this: two particles separated by vast distances are so deeply connected that the state of one instantly influences the other. This phenomenon, known as quantum entanglement, defies our everyday understanding of space and time. But what happens when one of these particles crosses the event horizon of a black hole? Does the connection survive, or is it severed forever? This question has puzzled scientists for decades. On one hand, the event horizon of a black hole is often described as a point of no return, where nothing, not even light, can escape. Yet, entanglement suggests a bond so fundamental that it might transcend even the extreme gravitational pull of a black hole. Some theories propose that entangled particles could remain connected across the event horizon, challenging our understanding of how information behaves in the universe. Others argue that the intense forces within a black hole could disrupt this delicate quantum link, leaving us with more questions than answers. The implications of this debate are profound. If entanglement can persist across the event horizon, it could reshape our understanding of black holes, quantum mechanics, and the very fabric of reality. It also raises intriguing possibilities about the nature of information and whether it can truly be lost in a black hole, a concept that ties back to Stephen Hawking's famous work on black hole radiation. As we explore these ideas, we're not just studying black holes, we're pushing the boundaries of our knowledge about the universe itself. This exploration naturally leads us to another mind-bending concept: the role of black holes in the study of the multiverse. Could these cosmic phenomena serve as gateways to other universes, or perhaps as evidence of their existence? The answers to these questions might lie in the strange interplay between quantum mechanics and the immense gravitational forces of black holes, opening up new frontiers in our quest to understand the cosmos. Now, let's take a step into the mind-bending realm of black holes and the multiverse. If the idea that our universe might just be one of countless others wasn't already fascinating enough, consider this: black holes could be the cosmic gateways that connect these universes. It's a theory that has captivated scientists and sci-fi enthusiasts alike, and for good reason. The intense gravitational pull of a black hole doesn't just warp space and time, it might tear a hole through the very fabric of reality, opening a pathway to another universe entirely. Think of it like this: if our universe is a sheet of paper, a black hole could be a puncture in that sheet, leading to another sheet, another universe, stacked beneath it. This idea stems from the concept of wormholes, hypothetical tunnels through spacetime that could link distant points in the cosmos or even different universes. While wormholes remain theoretical, black holes offer a tantalizing possibility that nature might have already built these bridges for us. But what does this mean for the multiverse? If black holes can act as portals, they might not just be destructive forces, they could also be creators, birthing new universes as they collapse. Some theories suggest that the singularity at the heart of a black hole might not be the end of everything, but the beginning of something entirely new. It's a thought that challenges our understanding of existence itself. As we ponder the role of black holes in the multiverse, another intriguing question arises. Could these cosmic anomalies also hold the key to understanding time loops? If black holes can warp time to such an extreme degree, might they create conditions where time folds back on itself, allowing for the possibility of time travel or even closed loops? It's a concept that bridges the gap between science fiction and theoretical physics, opening up new avenues for exploration. What if time itself could twist and fold, creating loops that defy our everyday understanding of cause and effect? Near the edge of a black hole, this might not just be science fiction, it could be a theoretical reality. Imagine a phenomenon called a closed time-like curve, a path through spacetime that loops back on itself. In this strange scenario, an object or even a person could travel along this curve and end up back at the same point in time, effectively creating a time loop. Sounds like something out of a movie, right? But in the extreme gravitational environment near a black hole, such curves could theoretically exist. The idea of closed time-like curves brings up some mind-bending questions about time travel and causality. If you could go back in time, would you be able to change the past? And if so, what would that mean for the future? These questions aren't just philosophical, they challenge the very foundations of physics. In fact, they've led scientists to debate whether the laws of nature might somehow prevent these loops from forming, even if the math suggests they're possible. It's a puzzle that keeps researchers on the edge of their seats. What makes this even more fascinating is how it ties into our understanding of time itself. Time as we experience it seems to flow in one direction, a concept often called the arrow of time. But near a black hole where gravity warps spacetime to its limits, this arrow might not be so straightforward. Could black holes hold the key to unraveling the mysteries of time's direction? This question pushes us into the heart of some of the biggest challenges in physics, where the behavior of time under extreme conditions could reshape our understanding of the universe. Black holes are cosmic enigmas that don't just warp space, they also twist our understanding of time itself. In our everyday lives, time moves in one direction, forward. We can't rewind it and we can't stop it. This irreversible flow is what physicists call the arrow of time. But when it comes to black holes, this familiar concept begins to unravel. Near a black hole's event horizon, gravity is so intense that time slows down dramatically. For an outside observer watching someone fall into a black hole, it would appear as though time for that person has nearly stopped, stretching seconds into what feels like eternity. Yet, from the perspective of the person falling in, time continues as normal. This bizarre contradiction raises profound questions about the nature of time and whether it remains a one-way street in the extreme environment of a black hole. Even more intriguing is what happens inside a black hole. According to Einstein's theory of general relativity, the singularity at the heart of a black hole represents a point where the laws of physics break down. In this realm, the arrow of time as we know it might cease to exist altogether. Some theories suggest that time could become so distorted that it loses its direction entirely, creating a state where past, present, and future merge into an incomprehensible tangle. This challenges not only our understanding of time, but also what it means for the universe's ultimate fate. If black holes can bend or erase the arrow of time, could they hold clues about whether the universe itself is destined to end in heat death, a big crunch, or something entirely unforeseen? These questions take us to the edge of what we currently know, and perhaps to the brink of discovering entirely new physics. As we ponder the mysteries of time and black holes, another fascinating puzzle emerges: the question of information. What happens to all the data about matter and energy that falls into a black hole? Does it vanish forever, or is it somehow preserved, defying the laws of quantum mechanics? This leads us to the next chapter of our journey, the concept of black hole information retrieval, a topic that has sparked some of the most heated debates in modern physics. The answers we seek might just redefine our understanding of reality itself. So, if information can't escape a black hole, is it truly lost forever? This question has sparked one of the most intriguing debates in modern physics. Enter the concept of black hole complementarity, a theory that suggests information isn't lost but rather encoded in a way we don't yet fully understand. Imagine a book that's been shredded, its pages scattered and seemingly destroyed. Yet, if you had all the pieces, you could theoretically reconstruct it. Black hole complementarity proposes something similar. The information swallowed by a black hole isn't gone, but is instead stored on its event horizon in a scrambled form. This idea challenges the information paradox, which arises from the clash between quantum mechanics and general relativity, both of which suggest information should be conserved. Black hole complementarity offers a potential resolution by suggesting that the information is preserved, just not in a form we're used to. And this isn't just a theoretical curiosity, it has profound implications for our understanding of the universe. If information is stored on the event horizon, it ties directly into the concept of the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary. Black holes, in this view, might be the ultimate test case for this principle, acting as cosmic laboratories for studying how information manifests in the universe. It's a mind-bending idea that pushes the boundaries of what we thought was possible, and it's reshaping how we think about space, time, and the very fabric of reality. Black holes aren't just cosmic vacuum cleaners, they might hold the key to understanding the very fabric of reality. Let's revisit the holographic principle, a mind-bending idea that suggests our three-dimensional universe could actually be a projection of information stored on a two-dimensional surface. It's like imagining the entire contents of a 3D movie encoded on a flat screen. Now, what do black holes have to do with this? They're thought to play a starring role. The event horizon of a black hole, the point of no return, could be that two-dimensional surface where all the information about what falls in is stored. It's as if the universe itself is using black holes as cosmic hard drives, encoding everything in a hologram. This idea gets even wilder when you consider the universe as a whole. Some theories suggest that everything we see, from stars to galaxies to ourselves, might just be a holographic projection of information stored at the edge of the cosmos. Black holes, with their immense gravitational pull and mysterious interiors, could be the ultimate testing ground for this concept. They challenge our understanding of space, time, and reality itself, forcing us to rethink what we thought we knew. As we wrap up our journey to the edge of black holes, let's reflect on the key mysteries we've explored. What exactly happens at the event horizon? Where does all the information go when it's swallowed by a black hole? And could the universe itself be a hologram, with black holes as the gatekeepers of this cosmic code? These questions remind us that the universe is far stranger and more fascinating than we can imagine. Black holes aren't just objects in space, they're windows into the deepest secrets of existence. As we reach the edge of our journey today, let's take a moment to reflect on the incredible mysteries we've explored about black holes. We've seen how the event horizon marks a point of no return, where time and space behave in ways that defy our everyday understanding. We've considered the mind-bending effects of spaghettification and the enigmatic role of singularities, places where the laws of physics as we know them seem to break down entirely. These phenomena challenge not only our scientific knowledge but also our very perception of reality. They remind us that the universe is far more complex and mysterious than we often assume. And yet, each mystery sparks new questions, driving scientists to push the boundaries of human understanding. What lies beyond the event horizon? Could black holes be gateways to other dimensions or cosmic shortcuts we've yet to comprehend? These unanswered questions keep us curious, reminding us that the pursuit of knowledge is as infinite as the cosmos itself. So, what do you think about these profound mysteries? How do they shape your view of the universe? Share your thoughts in the comments. I'd love to hear your ideas. And if you're as fascinated by the wonders of space as I am, don't forget to subscribe and join me on this journey of discovery. Together, let's keep exploring the infinite mysteries that make our universe so extraordinary.